Okay, good morning, all of you. Welcome to this lecture of refrigeration air conditioning. Last lecture, we have studied vapor compression cycle, its types. Okay, so I'm facing some network issue, so it is back now. So I'll just reconnect, wait for 2 minutes. So in last lecture, we have studied types of vapor compression cycle. So vapor compression cycle, before that we have studied Bell-Coleman cycle. Before that we have studied reverse Carnot cycle. Okay. So vapor compression cycle, it consists of two isobaric processes, one isentropic and one isenthalpic. So what are its types? So first is dry saturated vapor after compression. So I'll go through it once again. So first was dry saturated vapor after compression. So it is in the name. Okay, so what it says after compression. So we have this figure P versus H, pH and TS diagrams, and point 1 is end of evaporator. So that will be start of compression. Point 2 is end of compression or start of condensation. So what it says after compression, that means at point 2, the state of refrigerant is dry saturated vapor. So we have two curves. So this one is saturated liquid curve and this one is saturated vapor curve. So that point 2 should lie on saturated vapor curve. So that is meaning of this dry saturated vapor after compression. So we draw that diagram. Then there are this equation for COP of the refrigerator. So in all case, that formula will remain same. It will be refrigeration capacity divided by compressor work. Okay. So that is the formula for COP, coefficient of performance. Next type we have seen, that is the superheated vapor after compression. Again, after compression, that will be point 2, and that point 2 should be in superheated region. So superheated region is right of saturated vapor curve. So we have here saturated liquid curve. Again, we have saturated vapor curve. Superheated region lies on right of saturated vapor curve. Okay. So that point 2 should lie on this superheated region. So this is a superheated region. So then we get this TS and pH diagram. So superheated vapor after compression. Then similarly, I have derived this equation for COP. So in all cases, that will be same. Only the thing is that point will lie either on a saturated vapor curve or inside or outside of saturated vapor curve, inside or outside of saturated liquid curve. Next, we have superheated vapor before compression. So before compression, that means end of evaporator. So that will be point 1. So point 1 will be end of evaporation or start of compression. So that state of refrigerant should be superheated vapor. So that should lie on the right side of the saturated vapor curve. Okay. So as you see, that point 1 lies on the right side of this saturated vapor curve. Okay. Then we have this formula for it, COP. Then in this case, H1 and H2, we cannot directly calculate from that refrigerant chart. So for that, we need these two formulas here, H1 and H2. So that will be H1 is equal to Hg1 dash. So that is the enthalpy at point 1, this point 1, plus Cp delta T. Okay. Similarly for H2. Next, last time we had that was undercooling and subcooling. Sorry, that should be or undercooling or subcooling of the refrigerant. So in this case, what it means, subcooling means cooling the refrigerant below its saturation temperature. Okay. So saturation temperature for liquid, that should be 0.3 dash on the diagram. So here, so this is the 0.3 dash, that is the saturation temperature point. If I cool further below, so that will be 0.3. So here I will get 0.3. So that is the subcooled refrigerant. Similarly, if I show on TS diagram, so see here, point 3 dash, this is your saturation temperature T sat. If I cool below it, so this is I have cooled it here. So this will be called as sensible cooling. So point 3 will be subcooled refrigerant. So that is a difference between superheated and subcooled. Superheated will be in this region, okay? Subcooled will be in this region. If I say wet refrigerant, so that will be here. So this inside region, that will be wet, okay? Again, in this case, that formula, it is same, H1 minus H4 divided by H2 minus H1. Okay, H1 minus H4, it is a refrigeration capacity. This is the difference between these two enthalpy, sorry, not this is the entropy. These two enthalpies, H1 minus H4 will be a difference between these two enthalpies. So that is a refrigeration capacity. And H2 minus H1, so this H2 minus H1, that will be compressor work. Okay, so this will be compressor work. This will be QL, that is a refrigeration capacity. Okay, so this symbols what I am using here, QL, for refrigeration capacity. You may find different symbols in different books, so don't get confused because these symbols are not standard. But just remember the concept. QL stands for, in our case, it is refrigeration capacity. If I say QH, QH will be heat rejected to the atmosphere. Okay, WC is a compressor work. If I take WE, that will be expander work. Okay, so today we'll start solving the numericals. So this is the last part of first chapter, numericals of VCC. Then we'll see some like advantages and disadvantages. So that will be the last part. Okay, so symbols used. So before we go further in this VCC, so I want to first clear some symbols in this. So this is, suppose this is a pH chart, pressure versus enthalpy, and this is suppose one pH curve, it is there. Okay, so if I like start hitting one refrigerant from this position, you suppose first it is a saturated liquid. Okay, so at this point, okay, suppose pressure is here, it is pressure, it is P1. So at this point, the enthalpy, whatever enthalpy we have, that we refer it as a HF. Okay, so that will be enthalpy HF. Now I'll hit that, I will supply some enthalpy to that refrigerant. That will come to this point, that is a saturated vapor. At this point, I am notifying that enthalpy as Hg. So the enthalpy of gas, because here it was liquid. So liquid, here it was liquid plus vapor, and here it is completely converted into vapor. Okay. Now, whatever difference between these two, HF and Hg, that I am notifying it by HFG. So this you might have studied in applied thermodynamics, steam power plant. Okay, in that numericals, these notations were there. So same notations we are using here, HF, Hg, and HFG. If I take for entropy, that will be same again, SF, Sg, and difference between these two will be SFG. Okay. Again, for this process, that corresponding temperature, we call it as a saturation temperature. Saturation temperature at which this phase change takes place. So it is responsible for, no, it is present in phase change. Generally, we give that notation as Tsat, saturation temperature. Okay, I think this is kind of sufficient. Okay, if I take specific volume, that will be again Vf, that will be Vg, and this will be VFG. Okay. So please remember these notations because we are going to use it directly in the upcoming numericals. And if your refrigerant lies somewhere here in between, suppose here it lies, so we have some dryness fraction associated with. So let us say dryness fraction, we give it as a X. Okay, dryness fractions means like it starts converting from liquid to vapor. So X at liquid, it is 0, and at vapor X is equal to 1. Its dryness is increasing, so that dryness is indicated by dryness factor or dryness fraction. So these are the notations. I hope you have understood it. And we'll now move towards our numericals. Okay. So this is our first numerical. I will read it. So 28 tons of ice from and at 0 degrees Celsius is produced per day in an ammonia refrigerator. So in this case, our main objective is to produce ice. So this may be an ice factory, and refrigerant we are using in this case is ammonia. The temperature range in compressor is from 25 degrees Celsius to minus 15 degrees Celsius. So this range means higher temperature will be temperature of condenser, lower temperature will be temperature of evaporator. The vapor is dry and saturated at the end of compression. So this condition is given in this case. An expansion wall is used. There is no liquid subcooling. Okay, it is clearly mentioned there is no liquid subcooling. Assuming actual COP of 62% of the theoretical, calculate the power required to drive the compressor. Following properties of ammonia are given. Okay, so in that cable, first column, this is temperature. Temperature means that is a saturation temperature. Then enthalpy is given. So this liquid means that will be HF, and for vapor it will be Hg. Entropy is given for liquid, that will be SF. For vapor it will be Sg. So what they have given for this saturation temperature 25, they have given HF and Hg, and SF and Hg. For this saturation temperature minus 15 degrees Celsius, they have given this enthalpy and this entropy values. Okay. Latent heat of ice is given at 335 kilojoule per kg. So this is the given data. Okay. So please read this again, because I'm going to next slide. In that I will explain. I will show it first on pH and TS diagrams. Then we will solve. So this table is given in the book RS Kurmi. Directly they have given the values. But if they are not given the table, then what to do? Okay. So in industries, if you work on this system, they won't give the direct HF and SF values. Then in that case, we have to make use of refrigerant chart. So quickly, I will show you this refrigerant chart for ammonia. So what you see on the screen, that is a scan copy of that book. So what we are dealing here, it is ammonia, okay, NH3, properties of liquid and saturated vapor. So in this case, it starts from minus 60, and the values are given for HF, Hg, SF, Hg, and VF, Vg. Corresponding saturation pressure is also given here. So our case temperatures are 25 degrees Celsius and minus 15 degrees Celsius. So I'll quickly go to minus 15 degrees Celsius. Okay. Here I'll make one bracket. Okay, so this is the corresponding row for minus 15 degree Celsius. So as you see here, corresponding pressure is 2.37, corresponding HF is 131, corresponding Hg is 1443.9. So if you compare this value with this, so see here, the enthalpy is given 112, here it is 131. Okay, so here it is 131, and in this given example it is given as 112. So you cannot fully trust on RS Kurmi book. Okay, so it is not even internationally recognized. So outside, if you go, like, they don't recommend RS Kurmi book, because that is just a compilation of all the knowledge. But if you go for standard books, they will refer this refrigerant charts. Again, Hg in this case is given as 1443.9. So Hg here it is given as 1426.54. Okay, so there is a huge difference. If they give you these values directly, then you have no option. If they don't give you, then you have to use this refrigeration chart. Okay. Similarly, again, entropy here it is given as 0.742. SF is 0.742. Here it is given as 0.4572. Okay. and Sg in this chart it is given as 5.8223. Here it is given as 5.549. Okay, so Hg is like they have nearby values, but SFP is having huge difference. Okay, so this is I wanted to show you. Similarly, if you go for 25 degrees Celsius, so here it enthalpy HF is 298. Let us see how much it is there. So if I go for 25, yes. So here we have 25 row. So HF in this case it is 317.68. HF is 317.68. Here HF is given as 298.9. So there is a difference. Again in this case Hg is given as 1483.8.18. So in this case Hg is given as 1465.84. Slightly higher value is given here. Similarly, we can go for SF and Hg. So I think I have cleared my point that always depend on this refrigerant charts if you want exact calculation, right? So I'll go towards the solution. Let us first draw the TS and the pH diagram. So this is a basic thing here, pH and TS diagram. Now in this case, what they are given? They are given that the vapor is dry and saturated at the end of compression. So saturated means we have two conditions, either it be saturated liquid or it can be saturated vapor, but they have clearly mentioned that is a vapor is dry. Okay, so that means it will lie on saturated vapor curve. Okay, so the vapor is dry and saturated at the end of compression. That means at the end of compression we will lie here, somewhere here. So that will be our point 2, and then we can draw other points. So like point 1 will be here, 1. Okay, then it is assumed that after condensation there is no subcooling. They have given that there is no subcooling. So they are given that there is no liquid subcooling. Okay, that means that point 3 will lie on saturated liquid curve. So this will be point 3. Then that will be isenthalpy process, straight line. We'll get 0.4, and this way the cycle completes. Okay, so 4 to 1 it is evaporation, here compression, here condensation, and this is a isenthalpic expansion. Similarly, if I go for in this case, so here again that 0.2 will lie on saturated vapor curve, 0.2. Okay, so as this is isentropic compression, that there will be a straight line. This will be 0.1. Then we have 0.3 here. Okay, then this is the expansion process. Then the cycle completes. So this will be again evaporation, compression, condensation, and isenthalpic expansion. So this way I have drawn the diagram. Now first let us understand what is given in this case. So given what is given in this case. So they have given this temperature values. Okay, so this value is given. This value they have given 25 degrees Celsius. This value they have given minus 15 degrees Celsius. Okay, again they have given this value at this value they have given. So that will be at 25 degrees Celsius, we have to look for HF. Okay, so this will be HF at point 3. So that I think they have given that is a 298.9. And at point 2 also they have given the Hg value. So point 2 will be Hg. So that they have given at 25 degrees Celsius as 1465.84. So keep your calculus ready. I will need your assistance for calculating. Okay, so this they have given at minus 15 also they have given, but they have given this HF and Hg values. So they have given here and here. These values they have given. Okay, so I'll write down the given values. So let us say at 25 degrees Celsius. So they have given the H3, which is nothing but HF3. Okay, so H3 point that lies on saturated liquid curve. So that value they have given, that is the enthalpy of liquid. So that they have given, that is HF3. So HF stands for enthalpy of liquid, saturated liquid. So that they have given, that is in this case it is 298.9 kilojoule per kg. In this case, that H2 they have given. Okay, so H2 will be equal to Hg2. Hg stands for enthalpy of gas at point 2. So that they have given, in this case it is 1465.84. Okay, so kilojoule per kg. So this is the given data here. Next, what they have given? They have given the ice produced. So mass of ice produced. So like amount of ice produced. So let us say that notation I give as mass product of ice, that they have given as 28 tons. So that ton is unit of kg, sorry, mass in this case per day. So if I want to calculate kg per second, so I have to multiply 28 into 1000, because 1000 kg forms 1 ton divided by day. So in one day, how many seconds are there? So there are 24 hours into 3600. So can you calculate this mass flow rate of ice? So please calculate and tell me the answer. Okay, I think I was moved here. So okay, so I have calculated H4. Why H4 is equal to H3? Because it is an isenthalpic process. So that case it will be 298.9. So because H3 is given here. Next, our target is to calculate H1. See, H1 is that point 1 is in between saturated vapor curve and saturated liquid curve. So that is why the state of refrigerant at point 1 it will be wet. So here it is a wet refrigerant we have. That means we have to calculate the dryness fraction. Okay, once you calculate the dryness fraction, then you can easily calculate the value of H1. Okay, so H1 will be, in this case, it will be equal to HF. So it's corresponding HF here. So HF1 plus dryness fraction into HFG1. Okay, so in this case, HF1 it is given. How it is given? So at minus 15 degrees Celsius, they have given the enthalpy of liquid. How much they have given in this case? It is 112.34. 112.34 kilojoule per kg. Okay, and how to calculate HFG? HFG will be difference between Hg and HF. Okay, so I'll continue this on next slide. So we are in calculation of H1. H1 will be equal to HF1 plus X, that is a dryness fraction, into HFG1. So HF1, we know that how much it is. It is given, that is 112.34 kilojoule per kg. How to calculate HFG? So HFG is equal to Hg1 minus HF1. So how much Hg is given? So remember, in this case, we have to look for minus 15 degrees Celsius, because the corresponding saturation temperature for 1, it is minus 15 degrees Celsius. So in this table, we have to look for values of HF and Hg. So 112.34, it is a HF. Hg, that is the enthalpy of vapor, it is 1426.54. So it is 1426.54 minus 112.34. So can you calculate this? I think it will be straight away to 4. No, I think this will be the answer. Cross check, because I have just calculated while looking at the screen. So this will be HFG. Now the next thing is to calculate the dryness fraction. So X is your dryness fraction. Without this, you cannot calculate the H1. How to calculate the dryness fraction? Okay, I think it is wrong. It will be 413. Yes, yes. So I have corrected it. Thank you, Rohit and Asture. Okay, so next thing is to calculate dryness fraction. Now see here in this diagram how to calculate the dryness fraction. For that we have to take help of entropy. So 1 to 2, this it is a isentropic process. That means the entropy remains constant. And one advantage we are having now, it is that 0.2 lies on saturated vapor curve. So here that value of entropy. So value of entropy at saturated vapor, that is a Sg at 0.2, it is known. Okay, so it is given in this case. So that value will be equal to entropy at 0.1. Okay. So for compression process 1 to 2, in that case what happens, entropy remains constant. So entropy of S1 will be equal to entropy of S2, correct? So entropy of S2 is nothing but entropy of gas at 0.2. So let us see if it is given. So we have to look in this case for 0.2. 0.2 means that temperature is 25 degrees Celsius. So I have to look here 25 degrees Celsius, what will the entropy of gas? So that will be 5.0391. 5.0391. So this will be 5.0391 kilojoule per kg Kelvin. Okay. So that will be the value of S1 also. Now S1 will be equal to what? So S1, see here, the point 1 lies in the in between saturated vapor and saturated liquid curve. That means point 1 is state of refrigerant at point 1 is wet. So it has some dryness fraction. So S1 will be equal to what? Will be equal to SF1 plus some dryness fraction into that difference SFG1. Okay. So in this case, from the given, I have to calculate the SF1. So SF1 is the entropy of liquid at point 1. So I have to look for minus 15 degrees Celsius. Okay, minus 15 degrees Celsius and entropy of liquid. So that is, in this case, it is 0.4572. So that would be 0.4572 kilojoule per kg Kelvin. And SFG1. Now, how to calculate SFG1? So that will be straight away difference between vapor and liquid entropy. So SG1 minus SF1. Okay. Now to go again for which temperature? That will be minus 15 degrees Celsius, because point 1 corresponding temperature for point 1, it is minus 15 degrees Celsius. So I have to take the difference of these two values. So I have to take the difference of these two values. So that will be 5.549 minus 0.4572. Okay. I hope I remember that. 5.549 minus this SF value 0.4572. So what will be the answer in this case? So tell me the value of SFG. So Rohit, let us go step by step so that others will also will be with us. So tell me the value of SFG1. Okay, so SFG1, that will be 5 point. So as Rohit has calculated, I will take that value. Not because he has calculated, but there is only one answer I see. 5.0918. Okay, kilojoule per kg Kelvin. Right. So this time he has given the unit also. So good improvement. So yes, just I have to put these values there. So S1 we have calculated here, that will be equal to S2. So it is a 5.0391 equal to SF1. It is 0.45. Here SF1 it is there, 4572 plus X into 5.0918. So from this equation, you have to calculate the X. So how to calculate X? So I will take here on this side. So that will be 5.0391 minus 0.4572 equal to X into 5.0918. So can you calculate the value of X? So one person has calculated, others also calculate, and please check your answers. Okay, one more answer it is there. Others also please check if the dryness fraction is same. So Anna is given answer as a 0.899, so that is roughly equal to 0.9. Anna says that is my project student also. So like we are working a project which is related to our subject only, air conditioning. So I hope that project becomes successful, because last batch, because of this pandemic situation, we could not complete our experimental work. But let us see how things go. Okay, so I'll take that answer 0.899. So this way we have calculated the x value. Why we need x value? So I'll just take the revision here. So we are in calculation of h1. In that we had value of hf1, we had value of hfg1, but we didn't have value of x. So I now I can calculate the value of h1. Now h1 will be equal to, so hf1 here I have calculated, so that is not calculated, they have given directly 0.34 plus 0.899 into, so hfg here I have calculated, so that is 1314.2. So can you calculate the value of h1? So please do this sum. Tell me the answer. So h1, why others are not calculating? So should I ask one by one? So where is Pandre? Uh, I have seen him joining. Rohan. So Rohan, are you calculating? Okay, then tell the answer. This is a very simple calculation. I should have told you a difficult one. Okay, so this answer will be 1423.91 kilojoule per kg. So see here where we are now. So we have to calculate the COP of refrigerator. Okay. So in that case, first H2 was known, then we calculated H4, then the unknown was H1. So H1 was unknown. That also we have calculated. So just now we have to put the value in this formula. So you have to calculate the COP. Okay. COP will be equal to, so I'll write again. Sonalit Sawan has different answer. Rohit, why is it that? So Rohit, please cross check. You have given answer as 1423. So others are giving different answers. So Rohit, should I erase this answer? Okay, okay. So the correct answer I will take from the majority. So that will be 1293.8. So that will be the enthalpy H1. Now we can calculate the COP. So COP of refrigerator, in this case, it will be equal to H1 minus H4 divided by H2 minus H1. So don't get confused by what is H1, what is H2, how we have taken the formula. Just remember the diagrams pH and TS, the notations. H1 1 stands for end of start of compression, 2 stands for end of compression, 3 stands for end of condensation, and 4 stands for start of evaporation. Okay. So this is a refrigeration capacity QL. This is a compressor work. Okay. So if anytime you get confused, you just draw that pH diagram, draw that notation 1, 2, 3, 4, and you will come to know how to get the formula for COP. So put the values here. So H1 we have calculated now, that is 1293.8 minus H4. How much is H4? 298.9. 298.9 divided by H2. H2, where is H2? So here it is H2 given in the given in the example, that is 1465.84. 1465. How much it was? 1465.84 minus H1. So that is H1 again 1293.8. So what is the COP value in this case? So COP will be 5.78. So this is our first answer. Okay. So this will be your theoretical COP. Now they have given in the formula in the problem that the COP, actual COP is 62% of the theoretical. So COP actual will be equal to 62%, that is a 0.62% of COP theoretical. Okay. So how much it will be? So that will be, one answer it is a 3.58. Okay, so this will be your answer to. Okay, next thing is we have to calculate the compressor capacity. How much compressor work is required. So see here, they have given the latent heat of ice. So we have to design one ice factory. Ice is being produced at 0 degrees Celsius. So latent heat of ice is given at 335 kilojoule per kg. Now, in this case, we have calculated the mass flow rate of ice. It is how much we have calculated? 0.324. Okay, 0.324, 0.324 kg per second. So amount of heat required to remove from ice, or we generally call it as a refrigeration effect, or you can say amount of heat required to extract. So that will be, refrigeration effect will be equal to this latent heat into mass rate of ice. So 335 into 3.324. This will give you the value of refrigeration effect. Okay. So see here, the unit of latent heat is kilojoule per kg. Here unit is kilogram per second. If I multiply this, what will happen? So if I multiply this by kilogram per second, ultimately I will get kilojoule per second. So that is nothing but kilowatt. Okay. So unit of this, whatever value you will get here, that will be kilowatt. So may I know the answer? So it is Sirsat has given answer 108.54. So unit will be kilowatt. So why the unit is kilowatt? I think you have understood here. So if I multiply kilojoule per kg into kg per second, so that will be kilojoule per second. That is nothing but kilowatt. Now we have calculated refrigeration effect. We have the value of COP. Now we can easily calculate the compressor work. Okay, so COP actual will be equal to refrigeration effect divided by work required. Okay. So COP actually is 3.58 is equal to 108.5. Uh, Sorry, what was the answer? 54. 54 divided by compressor work. So this will be your answer. Whatever answer will be. So see, this unit is kilowatt, and COP doesn't have any unit. So unit of this will be kilowatt again. Okay. So response is good from your side. I'm very thankful to that. Good. So the answer is 30.32. Okay. So I'll just quickly revise what we have done actually, because we have done so many calculations that you may get lost. So I'll just take a revision. So we are in, we have to design one ice factory which has to produce 20 tons of ice per day at 0 degrees Celsius. We have condenser pressure 25 degrees Celsius. We have evaporator pressure minus 15 degrees Celsius. Then we have to use the refrigerant chart and calculate the enthalpy and entropy values. So we started with this pH and TS diagrams. Okay. Always draw this diagram. These diagrams will give you more clarity. Then I have written the given data. Okay. So so our objective was to calculate the COP. So in that case, H2 was given and H1 and H4 were unknown. Then I calculated the H4. Then there was calculation of H1. One point was lying in between these two curves. That means it was wet. So it has some dryness fraction. So we don't know that dryness fraction. For that, we have taken a help of isentropic process, and we have assumed, so isentropic means S1 will be equal to S2. From that, we have calculated the value of dryness fraction. From that, we have calculated the H1, and then we have calculated the COP. So this was our COP. So it was given that it was 62% of this theoretical COP is our actual COP. So we calculated 3.58 here. Then they have given this 28 tons of ice per day. I have multiplied it by its latent heat, so we get this refrigeration capacity. So from this refrigeration capacity and this COP actual, we have calculated the compressor work. So that will be work required in the system. Okay. So in next lecture, we'll solve a problem related to superheating and subcooling. So two more problems I will take. I will try to take a lecture of 2 hours, so that way we can complete this. Okay, so that's it for today. I request you to solve examples related to this. So you can Google it, vapor compression cycle examples, and you have to practice it. Unless you practice and use this refrigeration chart, you won't get a hand on this. Okay. So quickly, I'll just take attendance. Then we can stop.